introduce friend and colleague Jason Fleischer from Princeton University, Department of Electrical Engineering. Jason received his bachelor's degree in physics from U Chicago and his PhD in physics from UC San Diego. He was a Lady Davis postdoctoral fellow at the Technological Institute for Technology. He's been in Princeton since 2004, fellow of the OSA. Jason's published quite a few papers in Nature of Physics and Nature of Photonics. With a theoretical physics background, he introduces some interesting concepts into optics pertaining to fluid dynamics and plasma physics and a whole host of other things. He's here today to talk to us about nonlinear and quantum phase retrieval.
Great, thank you. Hey, good afternoon, everyone. It's a real pleasure to be back here, especially in the spring. So thanks for cooperating. I do want to talk about nonlinear quantum phase retrieval, a little more on the basic physics and imaging side, a little less on the abuse of language side. But I do want to start off with a little bit of philosophy, get us going on the same page, and remind you that all the limitations that we normally think about with imaging, resolution, field of view, depth of field, everything like this, comes from linear theory, right? And the classical linear theory in particular. So as soon as you violate that, you go nonlinear, you go quantum illumination, of course you can break all of these limits. Right? That's essentially it. Okay, that's a take-home message. So if you're hungry right now, you pretty much take off because the rest is details. Okay, the rest just follows. So if you want to stick around, what we're going to do is we're going to talk about this in more detail. A little bit of theory, tell you how we do nonlinearity using crystals and their response to light. So remind you of how we get there from the linear basis. I'll focus on spatial nonlinearity because we're talking about images. We want spatial modes and so forth. And then from this nonlinearity, we generate entangled photons and we get quantum optics. Leads straight into quantum imaging. Okay. I'll compare with linear theory, that's our groundwork. Talk about the mathematical problems of phase retrieval and what happens when these modes start interacting because there's some non-trivial math involved, a lot of which is still unknown. So and primarily there's a lot of issues with convergence. And then experimentally and of course computationally, we want to go digital. And in particular get out of the physical world and into something that's electro-optically controlled so we can have as many degrees of freedom as possible. And then go to the ultimate limit, which is quantum. Give you a very quick overview of what's fascinating about quantum phase, little tricks of the trade, and the benefits that you get from entangled photons. Okay, begin at the very beginning. Okay, this we all know, but what I want to emphasize is that what you want to focus on in Maxwell's equations and light propagation is entirely up to you. Okay. If you're fond of spatial pictures like I am, you want the spatial derivatives. This is your extended content. If you like pulses, you're talking about time variation, or maybe you like materials and manipulating light and looking at the index of refraction. Either rooting around for it like a truffle, or designing it yourself like a bed of material, something like that. This is what we learn in grade school. Right? You have some sort of dielectric material, an electric field comes across, separates out the charges, you get a little polarization response. This is just like Hooke's law, right? Linear case, you get a little displacement of the little charges, and if the material is a bit more complicated, then the response you get in X may be due to applied fields in Y and Z and so forth. So it's a matrix, or more properly a tensor response to get linear polarization. Okay. We also know about Taylor series. Right? There's no reason to stop at this first term. We can just keep going. X squared, X cubed, and so forth, right? Which means E squared, E cubed. This is intensity. And now your polarization depends on how strong your field is. All of these terms here that are not linear are nonlinear. Okay, because we're not really clever with our names. Okay, that's it. And the beauty part is, as soon as you put in something exponential, e to the I phase, we know that when you square it, phase just adds. You get twice the frequency, 3 times, and so forth. Okay? So that the color you get out is not necessarily the color you put in. And almost all of nonlinear optics boils down to simple addition and subtraction like this. Okay, so here's an example. You take, in this case, a green laser pointer, just like I have in my hand, right? And it's a little expensive to create green light because it's higher energy. So what you do is you start with red, or in particular infrared. You put a nonlinear crystal here, 1064 gets doubled into 532, green light comes out. Okay? 1 plus 1 equals 2. As easy as it gets. If you're a little more creative, right, you go backwards. You start with a high energy photon, and you split it into 2. Okay, conserving energy and conserving momentum. In this case, momentum is the direction here, which you can tune by tuning the orientation of the crystal. And what you see with these 2 photons, they're actually born at the same time in the same place. And right here where they overlap, you don't know whether the intensity has a contribution from the upper or lower photon. There's some ambiguity there, or some entanglement, if you will, a special kind of correlation. Most of quantum optics starts in nonlinear optics generated by these crystals. So first I'll discuss this, and then later on we'll see what happens with that. Now nonlinear optics, for imaging, almost always deals with frequency. Right? You change the color. There's a variety of reasons for this. So here's, for example, 2 photon absorption. You have the normal focusing of a beam. So this is the Rayleigh range. In this case, you have fluorescence, so it lights it up. You can see it rather pretty. If there's 2 photon absorption, the intensity is only high enough in the center, or if you like, the photon density is only high enough, that absorption is most likely the focus and nowhere else. So from this higher order or nonlinear process, you immediately get 3D information. If you're talking about going through tissue or something scattering, we know that shorter wavelengths scatter more. So it's nice to have longer wavelengths to go in and penetrate. You convert. Shorter wavelengths give you higher resolution. And then they only have to go one direction back to your detector and not a round trip. So you win twice. Scatters less, higher resolution. And in bio, you can start labeling these things and separate out cell wall from nucleus and so forth. And it's all based on these additions conserving energy. Stick an H bar in front of there, and everybody's happy from a physics sense. Now, you also have to conserve momentum with these wave vectors. And this is where things get complicated, because these are your Fourier modes. These are all spatially extended. And historically, this has been viewed as terrible for imaging. Because if you mix up your spatial modes, if you add and subtract, the spatial modes that make up your picture change at the end of the crystal and give you something that's totally distorted. And this looks bad for imaging. Okay? Philosophically, you might argue that nothing's all bad. Okay? It's a physical effect. Let's understand it, and let's engineer it. But it does raise the question of why you want to do this in the first place, because we have plenty of materials that we can actually look through. Right? Glass, plastic, contact lenses, and so forth. Why go out of your way? Right? Why would you do something like this? Well, first, it's a good way to characterize your material. Right? If you put something known in and you measure the output, you can kind of get a feel for what it's doing. You can explore the dynamics if you have some pattern here that you want to watch interact. And eventually, you want to use it for imaging. Now, a lot of my work, especially in the past, has been on basic wave physics. Light's a perfectly reasonable wave, and it's very friendly, right? Because you can control the input and directly take a picture of the output. So anything a wave does, light can do. So if you're fluid-minded, for example, in mechanical engineering, you can look at diffraction around a wire and treat its flow around a cylinder. That should roll up into vortices, which it does. You get shock waves bouncing off the front. You can get instabilities. You can get turbulence. All sorts of things. If you're like statistical, like from the sun or coming out of a projector, you have a statistical fluid or a plasma, and you can do all sorts of plasma physics that you can't actually do in a material system, because you have ions floating about, for example, that shield out any attempt to probe the inside. In optics, you have things like holography, where you can measure the volume dynamics. And if you're using statistical light, you can go as crazy as you want with statistical physics. You can look at thermodynamics, you can look at phase transitions, and so forth. You just take some statistical pattern coming in, there's a different statistical pattern coming out because all of these modes interact, and you do thermodynamics on it. Look at the entropy. Not only the physical entropy, with all of this randomness, for example, creating coherent structures, again, maybe you're information-minded, and you want your randomness to be noise, and your coherent part to be signal. And loosely speaking, when these modes interact, noise and signal talk to each other. And that's really what I want to focus on as part of the broader category of computational optics or computational imaging, where the idea is, if you put extra information about your system, it's a system. So if you put, say, replace your aperture with something coded over here, perhaps get more information about your object somewhere down the transmission line. Better resolution, 3D depth of field, something like this. And there's all sorts of ways to do this with wavefront coding and mask, structured illumination, and so forth. And what I want to add into the mix is now nonlinear propagation. It's an extra physical effect. We learn about it, get the information for the physical part, transfer that to the object, and see where we're going. And all we're doing is starting off with our spatial modes, so the rays going off in certain directions, they add and subtract, give you different daughter waves. And this is what essentially it looks like in image. Normal image, we have some object that we shine light on, take a lens, and gather the rays into a camera. Let's just deal with ray objects. Some rays make it, some rays are lost. They don't quite get into the aperture, there's not enough index of refraction, something like this. And if you lose this ray, of course, you lose that information. Let's replace our lens with a nonlinear crystal. That ray here is still lost. It never makes it into the camera, but it adds and subtracts and makes a daughter wave. That ray does make it into the camera. If we know how this mixing happens, we can say, all right, there's our paternity test. That ray is the parent. So it must be here if we detected this one there. And there's a way of formalizing all this. It's through Abbe's theory. Okay, so we're going way back to the end of the 19th century. And the idea is that you have whatever object you have, you can split it up into Fourier modes, sines and cosines. In a linear problem, we can only consider one of them at a time. We're allowed, because superposition works. And this Fourier mode, if we shine light on it, looks just like a diffraction gradient. So we have different orders that may make it through our aperture. If they make it through, we see something. If they're blocked by the aperture, we don't. That's our resolution limit. So it depends on the aperture of our system and the spatial size or the wavelength of this mode, right here. And you can see it over here, with an extra factor of 2. If we replace this lens with a nonlinear material, again, we miss those rays, but all of these daughters are created. Some of them get into our camera, and we see something. It's not the original periodic pattern, it's something different, because it's a different mode. But if we understand this mixing, we can deconvolve this and figure it out. And this is roughly how it works. We have some numerical aperture that accepts rays. One of those rays is beyond that limit, so we don't see it. But because this mixes, we get this in here. It's basically an interference process. Those two waves create constructive and destructive interference. Inside the nonlinear material is an index change, so it makes a grating, and it bounces off that grating back into our window of observation. In other words, this is exactly what structured illumination does. If we have some limit to our aperture, which we always do, we can physically put a grating there in front of it and shift our entire pattern by the wave number of the grating, so that the tails here that we couldn't observe are suddenly in our window, and we can. In the nonlinear case, it's a circular argument, as all nonlinear arguments are. You send in these two waves, they add and subtract. The lower frequency part is in our window, and then those waves bounce off the grating they create into your window, and you detect it. So there's a whole bunch of elements to the method here. First, you need some nonlinear crystal here to work with magic. I'll explain that in a minute. You need to calibrate it so that you know what's going on with the nonlinearity. Come up with an equation so you can go backwards and say your object here must have been, your image here must have been due to your object, and then you want to apply image. So the crystal I use is very much like these sunglasses that get dark when you go outside, except instead of the opacity increasing, the index of refraction changes. And it's a rather complicated response, how charges get excited and shift over and create this electro-optic index change. The two things you really need to know are, it's sensitive to light, okay, so it depends on the intensity, and I can control how sensitive it is by applying a voltage across the crystal. That's completely up to me with these electrodes here. And in fact, I can make it focusing or defocusing simply by changing the applied bias. So it's a very friendly crystal. It responds to low power, milliwatts of power. Okay, so I actually could use this laser pointer and do the experiment, but it would take a long time. The flip side to nonlinear optics is using things like femtosecond lasers, so there's a denominator to give you high intensity in a short amount of time. I'm pretty patient for the most part, particularly post-tenure, so I can wait. Okay. So here's an example of sending light into a crystal. It's just a couple of waves here, so a background plus and minus k, and I watch what happens at the edge of my crystal. It's rectangular, so I can go a short distance and see my additions. Subtractions just overlap, no problem. Go the long way, and they add again. Keeping on adding higher and higher k's, smaller and smaller spatial frequencies, thinner and thinner lines. That's it. It's because of the exponential that these modes just add. And this is basically a spatial frequency cone that lets me measure things quite accurately. And for imaging, it all boils down to Abbe theory, so I can get those modes through my aperture and record something that I can then deconvolve. And here's a very simple experiment of how that works. The dotted lines here show my angle of view of my camera, so my numerical aperture. And the k values are outside of that. So in the linear case, I basically just see a plane wave here, little fringes for the crystal. In the nonlinear case, I get to see fringes. I get a daughter wave here that shows up, and I can tell if the daughter wave is here and my original beam is here, it had to be created by it was plus and minus. So in general, this is what we do. You take it, your image gets all distorted. We know now how these waves mix. Put it in a computer, run our numerical code backwards, and see if we can reconstruct the input. And in general, you might be hesitant to do this because nonlinear problems are very sensitive. Right? This is the whole idea behind chaos, for example, sensitivity to initial conditions. Okay? And of course, nonlinear problems aren't easily inverted. Right? If I ask you the square root of 4, and you've had your coffee this morning, you might actually say plus and minus 2. Right? There's ambiguity there. And the worse the nonlinearity, the worse the multiplicity of your answers. Okay? The beauty part here is this actually is not an inverse problem. I'm not asking such a thing. This is an initial value problem where my starting point happens to be my output, and I march one direction back towards my input. That is always unique. It might be sensitive, but it's always unique. And it turns out I work with the nonlinearity that's defocusing rather than focusing, so I don't go highly unstable. I flatten things out so that it's as well behaved as possible to give me the best answer I can get. And here's an example of how it works. This is experimental. So I take some object here, I try and image it, and what I'm going to do is just take a piece of cardboard and block the upper half of my resolution chart. So I no longer get those rays in my camera, I lose that information. Replace the lens with this nonlinear crystal, and what I measure is extra interference fringes. And my claim, of course, is that those fringes have extra information. And sure enough, when I do the deconvolution, these fringes are caused by this extra bar up here. If I zoom in on that, there's the extra bar. I have a very weak index of refraction change, 10 to the minus 3 on that order, even less. But that's enough to increase my field of view by, say, 30%. There are organic materials and polymers that are 100 times better than this, 10 to the minus 2 index response, which is like a 3,000% increase in field of view. Doesn't scale that way, but it's close. And the nice part is, because I'm nonlinear, I start breaking all of these linear rules. For example, in microscopy, it's well known there's a trade-off between how well you can resolve your sample and the contrast with which you can see it. In this case, I can get both, because not only do I have these high k's subtracting to get me into my numerical aperture here, but I also have the low k's scattering out. And in particular, the DC term. So if I'm weak contrast, I have a high background and a very small modulation, and I drop my background, of course my modulation shows up really well. And you can see that here. Very poor resolution, the modulation is very weak. When I scatter that DC term out, everything pops out. And I can get both at once. In fact, all of these things can happen at once. It's kind of magical. Okay. That was intensity. Now I'm going to switch to phase. And here's a typical way of modeling with a diffraction term, and a nonlinear term, kind of a split-step sort of method. And my claim, of course, is that nonlinear materials are going to be more sensitive to phase. The reason being, the material depends on the intensity. So if I shine light on it, the index of refraction changes. That index of refraction, of course, affects the phase velocity. That phase changes as it propagates, which changes the intensity, which changes the index again. Right? It's a back and forth circular loop here. So you get a double effect. It has to be more sensitive. Here's just a simple example, a numerical simulation of a square that linearly diffracts, but non-linearly you get this enhanced, if you will, Fresnel diffraction, all these extra fringes. And this clearly contains more information than this one does. And if you'll let me be a little anthropological here, right? Phase is key. Okay? Phase is what carries all your information. It's nice to have intensity because you know there's light around, but everything else is determined by where you are and where you're going from a mechanical sense, how fast you get there, where you start with, and so forth. Right? The complexity of your wave is in your phase. And it appears all over the place. Right? It's critical for biology. Cells are mostly water, so they don't absorb light very well. So if you just take a picture, often you don't see anything at all. You need some sort of phase contrast method to bring out the changes. Right? There's different thicknesses in your cell. Membrane nucleus in particular looks like a giant sphere. That's a lens. When you image the phase of a lens, it's just phase. It looks like intensity. If you back off a little bit, you focus, and you can see the light in the edges. Clear air turbulence, wind tunnel turbulence, and so forth. Now, with coherent light, there's all sorts of ways to get phase. Very easy. And in particular, we just use interference. Right? This is, I guess, now a high school experiment. If you're incoherent and you have a fluctuating phase, right, this is a lot more complicated to really get where the direction is going. Because if you think about it, when light is hitting the screen, for example, it's bouncing off in all different directions. So it's not a single direction of light coming at you, it's a whole ensemble of them. And we want to look at the envelope. Many ways of doing it because it's such an important problem. And it all basically boils down to how a lens works. You take a lens and a uniform wave coming on, and then at some distance down the line, let's call it a focal distance, right? You focus your light. You convert your phase, your flat phase front, to something spherical, and then the intensity changes. So we transport our intensity. Defocus a little bit, watch what the phase does to intensity, or if you want to go far field all the way, you do a Fourier transform, or anywhere in between. There's all sorts of options. Really, the key point is, at every point, you have an amplitude and a phase, so you need two measurements. And it doesn't matter what those two measurements are. Polarization, wavelength, or linear or nonlinear. Let's keep going. This was the first one. It was by Gertzberg and Saxton in the 70s, so 40 years ago or so. And the way they did it is they took a measurement of just the intensity. Then they put a lens, focal distance and focal distance, to do an optical Fourier transform. And this is convenient, of course, because you can do a numerical Fourier transform too. So you can combine the physical with the numerical in this computational optics problem. You don't know the phase, and you don't really know what to start with. So typically people just start with a uniform phase. You have an intensity pattern in a uniform phase, you Fourier transform that, and you get some sort of numerical amplitude and phase at the end. And then you physically measure the far field Fourier transform with the lens. Take your measurement and replace the numerical value. So you have a known amplitude, some numerical phase, inverse Fourier transform, so you get a numerical amplitude and phase here, but you've measured the amplitude. You replace it. So you go around the loop, Fourier transform, inverse Fourier transform, at each endpoint, replacing the numerical amplitude with the physically measured one. And hope that when you do this, your phase converges. Okay? This is a very abrupt thing to do in an algorithm. Okay? This is not a continuous, I'll do a little step and look at a little change. Okay? I'll go all the way and do a Fourier transform, and then out of my hat, take a measured value and stick it in there. Do something numerical, stick it in there, and hope that this works. It's a black box method. And a lot of times it doesn't work. It'll converge into something else, because phase is very complicated, and it may get stuck in a local minimum versus a global minimum, or a conjugate value. Or maybe it's just really slow to converge. You have no idea. If you do a numerical test case, you can watch this. You can watch the convergence process and see how your phase error is numerically in this process versus your known test sample. And you can see here, this is what you would measure on the outside, your numerical amplitude and your measured amplitude, and it's looking pretty decent. You're monotonically decreasing. But you reach a point of diminishing returns very quickly. There's no point in continuing on here. And for an unknown object, for a real kind of imaging problem, you would never notice. You'd never know when to stop. What I want to do is I want to generalize this now to something nonlinear. So I have my nonlinear crystal. I have some intensity here. I don't really know what it is. It's an unknown object. And I can only measure the output. But what I can do is I can tune the nonlinearity. I have this voltage in my crystal, so I can do different degrees, or I can make it on and off, for example, linear versus nonlinear. I'll measure the output, numerically propagate back, change my nonlinearity, numerically propagate forward, get some value in my computer, replace it with my experimental value, and then go back and forth, rinse and repeat, and hopefully I'm squeaky clean at the end. This is what the convergence looks like. Numerical amplitude, measured amplitude. The linear case was monotonic. The nonlinear case is extremely different. It's highly non-monotonic with this peak right here, which is kind of encouraging because maybe it correlates to something. And if you do a test case where you know what your phase is, it turns out that that dip here correlates to the minimum error you get in your phase. The actual phase that you want. It's kind of a resonance condition. And the reason it's a resonance condition is because you have all of these waves interacting, and the only way they cooperate is by phase matching. You have to conserve energy and momentum. That's a very strong condition. So that happens here at this peak value, and it tells you you're really in line with what you want. It's really rather remarkable. And because it's a nonlinear problem, right, you get this enhancement, this sensitivity. You get a far better result. Not only do you know where to stop, but your result is twice as good. Sometimes it's often 3 times as good, depending on the strength of your nonlinearity. So here's the experiment, where you have a lot of noise here, high level frequency and so forth, but again, your nonlinearity kind of cleans that up. It focuses in on the high frequency parts that are resonant, where everything's matched, and it scatters out the low frequency parts and gives you a nice noise behavior. And because it's nonlinear, it depends on intensity. Right? How well you do depends on how strong your light is. So there's actually some wiggle room here in tuning this guy. So you can be above or below the resonance, or in this Goldilocks condition where you're right on, right here. It's kind of a double resonance. The phase matching in the first place, and then the intensity to make things in line. And now this opens up a whole host of issues, right? This is the very simplest nonlinearity you can get. It's called pure nonlinearity. The index is proportional to the intensity, the E squared, that next term in the Taylor series. You have all the other terms in the Taylor series. You have any kind of mathematical function you want. And you have any metric you want. Right? In this case, I did phase. But it could be edge detection, it could be correlation, it could be resolution. Right? What is it about your problem that you want to optimize? What is it about the material that you want to use? Right? What is it about the algorithm that you want to modify? Because that's your freedom too. Right? You have 50 years of linear theory to leverage, and then all of nonlinear theory, in whatever field you want. Chaos and transforms and Hilbert spaces, machine learning if you like, and so forth. So if I look at my problem, I can tune everything and figure out a resonance. And it turns out, quite nice, what you really want to do in order to get the most bang for your buck, right, is inject as much information, as much new information as possible from your nonlinearity. So the best way this works is you take your linear measurement, you take your nonlinear measurement, and you adjust the intensity so that they're basically orthogonal as far as correlation goes. So the nonlinear part contributes the most to give you the best minimum possible.